This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Borczek, and today we will discuss 8 topics. The first topic is about Fedora, which aims for 99% reproducibility, which is the following article here. Fedora, a popular Linux distribution, is working on making 99% of its software packages reproducible by October 2025 with their version 43 release. But what does reproducible builds mean? It means that given the same source code, build environment, and instructions, anyone can create exact duplicates of the software program, the binaries that users run on their computers. When builds are reproducible, other people can compile the same source code and get identical results bit by bit. This allows independent verifications that the software you downloaded actually comes from the claimed source code and hasn't been tampered with during the build process. If they match exactly, it confirms no malicious code was inserted during compilation. Fedora started this work later than projects like Debian, which has been working on reproducible builds over a decade. Debian has achieved reproducibility for their live images, so 100% reproducible builds, but they do not have yet achieved complete end-to-end reproducibility for all their software packages and images. Fedora already reached about 90% reproducibility through changes to their build system, and now they want to reach 99%. There are some technical challenges. RPM packages include information like build time and build host in their headers, which can make exact reproduction difficult. Fedora has worked around this by clamping file modification times to a standard value and creating tools that remove non-deterministic information from files. To reach their goal, Fedora plans to add tools for developers to test reproducibility and set up a system called Rebuilder that automatically verifies that packages can be reproduced from source. They will also update their packaging guidelines to treat non-reproducibility as a bug that needs fixing. Some packages have known problems that make reproducibility difficult. For example, Haskell packages aren't reproducible when compiled by multiple threads, and Go packages contain debug data that varies even with the same input. And I think reproducibility build helps to mitigate supply chain attacks. It doesn't solve it, as it establishes a verifiable connection between source code, which can be independently audited, and the actual binary running on the user system. I'm currently using 3 distributions: Ubuntu, which is Debian based, Fedora, and Arch. And I also looked up Arch, which has almost 88% reproducibility on their packages. However, these percentages are difficult to compare between distributions because these distributions have different packages in their base system. But the trend is good, it's increasing, and I really appreciate that. The next topic is about WebSockets, and it's the following article here. This recent article discusses why developers might be using WebSockets for the wrong reasons and suggests alternatives. WebSockets create a two-way communication channel between client and server, allowing both to send and receive messages at any time. And we will also talk about this in one of the upcoming lectures. However, there are important limitations to consider. First, WebSocket messages aren't transactional. It's difficult to associate requests with their responses since all messages flow through the same channel. This makes error handling complex, especially when dealing with state changes that need validation. And what the author means by transactional, the messages, the request and response travel through the same channel without any built-in way to associate them. It's hard to know which response belongs to which request, but it's solvable. Second, managing the socket lifecycle adds complexity. Applications must handle connection opening, closing, reconnection attempts, and cleanup when connection ends. And this creates more edge cases to handle compared to regular HTTP request, but again, it's solvable. Third, implementing WebSockets make server code more complex by requiring HTTP upgrade, handling specialized connection protocols, and managing partial data frames. But again, it's solvable. The article suggests using HTTP streaming as an alternative for many real-time applications. HTTP was designed to stream data, and this article suggests that this can be used to create a one-way stream from server to client by combining regular HTTP requests for client-to-server commands with a streaming HTTP response for server-to-client updates. Developers can achieve real-time communication without complexity of WebSockets, so basically doing a request and keep the request connection open. I think this is very similar to servers and events. And the article includes code examples showing how to implement this pattern using JavaScript Stream API on both the server and on the client side, demonstrating how to maintain real-time updates between multiple clients without using WebSockets. I'm not yet sure what the benefits are compared to servers and events, which are also HTTP based. With WebSockets, for example, it's not straightforward to add, for example, JOT tokens, but again, this is solvable. And this is also why I'm curious about the experiences of my students that are required in their challenge task to use servers and events. So I'm really looking forward for their results. The next article is about vertical sharding. It's the following article here. And this article highlights the challenges of vertical sharding in database systems. Vertical sharding, also known as functional sharding, involves moving tables out of your main database into separate database instances to reduce load and improve scalability. While this approach does provide temporary relief for database load issues, it comes with downsides according to the authors. First, it reduces overall system reliability. Here's a nice calculation here. The article explains this mathematically. With a single database that has 99.95% uptime, your system uptime is also 99.95%. But when you add a second vertical shard that required for your operations, your uptime will drop to 99.90, as either database failing will cause a system failure. The second major problem is increased code complexity. What was once a simple database join become multiple queries across different databases with manual data combination and application code. This leads to bugs, performance issues, and development delays. Instead of a simple query joining users, orders, and products, the developer must now query the user database to get user information, query the order database to get user orders, extract product IDs from the orders, query the products databases using those IDs, and manually reconstruct the relationship between orders and products. And this fragmentation may lead to workarounds like duplicating data across databases or creating services that hide the complexity behind APIs, but these add latency and additional failure points. I think this article is a bit too negative, because if you have tables that are loosely coupled, then vertical sharding could make sense. This is the first step to encapsulate functionality that may be later moved in a separate service. The next article is about SSH keys. It's the following article here. This article highlights an important challenge in managing access to distributed systems. Traditional SSH key-based authentication doesn't scale well for large organizations. SSH is the standard way engineers remotely access Linux systems, but the traditional approach becomes problematic as infrastructure grows. The problem with SSH public key authentication is that it requires distributing and managing user public keys across every machine that needs access. This creates several challenges. First, key management becomes complex as the number of users and machines increases. Organizations end up with key sprawl, hundreds of keys scattered across infrastructure with no centralized way to track them. Second, it becomes difficult to maintain visibility over who has access to what. Administrators struggle to answer basic security questions like which user can access which machine. Third, user access provisioning and deprovisioning becomes a major operational burden, often leading to former employees retaining access because removing their keys from every machine is complex. And the article proposes here SSH-based certificate authentication as a solution. Instead of distributing individual keys, this approach uses a centralized trust model with certificate authorities. When a user needs access, they request a short-lived certificate signed by the certification authority. Servers are configured to trust any certificate signed by this authority. And the benefit here include you have a centralized management of access. There is built-in expiration for credentials, better visibility and auditability, and simplified onboarding and offboarding. And the article also mentions that major tech companies like Meta, Uber, and Google already use SSH certificate-based authentication for their infrastructure. And this is very similar to the approach with the access and refresh tokens that we discussed in lecture 8. I am not using such an certification-based SSH authorization system as I currently maintain 4 servers at the moment, and this can be done without such an infrastructure, but in large companies, this could make definitely sense. The next topic we also discussed in lecture 8, it's the following article here. This blog post dives into the inner workings of one-time passwords, OTP authentication systems that power many modern two-factor authentication solutions. The author explains how these systems generate those 6-digit codes and constantly changes in the authenticator app. The core challenge with traditional password is that they remain static. If compromised, they can be reused indefinitely. OTPs solve this by generating temporary codes that are only valid once for a limited time window, significantly reducing the risk of such attacks. The article explains 2 main OTP types: the HMAC-based one-time password. This uses a counter that increments each time a code is generated. Both the server and client share a secret key and know the current counter value, allowing them to independently generate the same code. And TOTP, time-based one-time password, this is essentially HMAC-based one-time password, but uses the current time as the counter, and this eliminates synchronization issues and makes code automatically expire, typically after 30 seconds. The technical implementation relies on cryptographic hash functions. So both server and client need to share the same secret key. The current counter or the time value is hashed using hash-based message authentication code, and the resulting hash undergoes a truncation process that selects a portion of the hash, and this value is then converted to a human-readable format, typically 6 digits. And what makes this secure is that even if an attacker intercepts a valid OTP code, they can't determine the underlying secret key or generate future codes. With TOTP captured, codes become useless after their short validity period. The beauty of this system is that the client and server can generate identical codes independently without transmitting the actual password over the network. They only need to synchronize once when setting up the initial shared secret. The author implemented their own OTP generator from scratch to better understand the underlying mechanism and published both the application and source code online. And this is, in my view, the best way to understand many detailed aspects by just implementing it. I really like this approach. The next article is about certificates. It's about TLS certificate lifetimes that will officially be reduced to 47 days. It's the following article here. The browser forum has voted to significantly reduce the maximum lifetime of TLS certificates over the next few years. This change will have major implications for how websites and services manage their security infrastructure. According to the recent announcement, certificate lifetimes will gradually decrease following this schedule. Until March 15th, 2026, the maximum lifetime remains 398 days. Before that, it was 825 days, and from March 2026, the maximum lifetime reduces to 200 days. 2027, the maximum lifetime reduces to 100 days. And in 2029, the maximum lifetime reduces to just 47 days. Apple, who proposed these changes, argues that shorter certificate lifetimes are necessary because information in certificates become less trustworthy over time and the current revocation system are unreliable. Browser vendors often ignore these revocation mechanisms, making it difficult to invalidate compromised certificates. By shortening the certificate lifetimes, the impact of a compromised certificate is limited. And the number 47, that was not chosen randomly. It represents approximately 1.5 months plus a little bit of wiggle room. So it's 31 plus 15 plus 1, it's 47. And the key takeaway is that these changes will effectively mandate automation for certificate management. Manual certificate renewal process will become impractical with such short lifetimes. The industry has been moving towards automated certificate management for years using protocols like the ACME, the Automated Certificate Management Environment, and these changes will accelerate that transition. Certificate authorities are preparing for the shift by enhancing their automation capabilities, and organizations that haven't yet adopted automated certificate management solution will need to do so well before the 2029 deadline. And we also were looking into the ACME protocol and Let's Encrypt in the lecture in St. Gallen with Caddy, where we identified a problem with the ENS DNS server infrastructure. We could not fix the problem, but knowing the details of the problem, we could find a workaround. So we also played with these automations, and it's quite interesting, I have to say. In any case, these TLS certificate lifetimes should not impact an end user too much. For regular use, when you browse the internet, your browser will automatically renew the certs since your browser is online anyway, so there's no impact. If you have kind of an esoteric use case where you need, for example, to verify a certificate locally without being online, then you need to reconnect to the internet every 47 days to let the browser refresh the certificates. The next topic is about DeepSeek's distributed file system. It's the following article here. This blog post introduces 3FS, Fireflyer file system. It's also tough to pronounce this. And it's a new distributed file system released by DeepSeek. Distributed file system allow applications to interact with files spread across multiple machines as if they were accessing local storage, creating a powerful abstraction layer that hides complexity from users. The primary advantage of distributed file system include the ability to store massive amount of data, petabytes, provide higher throughput than single machines, and offer fault tolerance and redundancy. And these systems commonly used in parallel processing frameworks, machine learning, training pipelines, large-scale code repositories, and photo storage services. And this 3FS consists of 4 main components. It's the meta nodes. They manage metadata such as file location, properties, and path, and this is based on the foundation DB. They have management nodes. This controls the cluster configuration, tracking which nodes are alive and their locations. They act like routers that help nodes find each other, and storage nodes hold the actual file data managed on physical disks, breaking it into chunks managed by a Rust-based chunk engine based on LevelDB. And various workers allocate, reclaim, and process read-write operations on these chunks. And the last one are the client nodes. They communicate with all other nodes to view and modify the file system. They discover nodes through the management node, perform file operations via the meta servers, and transfer data via the storage nodes. And a key feature of 3FS is its implementation of they call it chain replicated with proportionate queries, which is shown here, how this works. So this is a protocol that claims achieving strong consistency. In this system, write begins at the head of the chain of node, propagate to the tail, and then commit messages travel back. And this provides a fault tolerant, but comes with trade-offs. Write throughput is limited by the slowest node in the chain. And it works like this. So here it arrives, then the write propagates, and when the write propagates, it sets its state to dirty. If it reaches the tail, it sets its states to clean and propagates this back to the head, and also then sets this state to clean. And with that, they achieve strong consistency. The block order notes that while many distributed file systems share similar high-level components, the difference in their approach is that while many distributed file systems share similar high-level components, the difference lies in their real-world performance characteristics, tuning flexibility, deployment simplicity, and reliability. They also plan to test 3FS extensively and evaluate its performance claims and compare it with other distributed file systems. The last article is about blockchains. It's the following article or the following guideline here from the European Data Protection Board. And this board has released a new guideline on processing data through blockchain technologies. These guidelines address the tension between blockchain's fundamental properties and GDPR compliance. We will talk about blockchains, but the key property of a blockchain is that the data is immutable, while GDPR mandates that data needs to be removed on request. And the document acknowledges that blockchain technologies can offer strong technical guarantees for data integrity and availability, but also creates specific challenge for data protection compliance. The distributed and append-only nature of blockchains make it difficult to implement principles like storage limitations and data subjects right, such as erasure and rectification. And the guidelines provide several key recommendations. First, regarding architecture, organizations should document why blockchain is necessary for their specific data processing needs. They should favor private permissioned blockchains over public ones when possible. Well, in my opinion, that's not a really good recommendation because private permission blockchains have proven to be pointless and they're not widely used at the moment. Second, personal data storage should be minimized on-chain. The guidelines strongly discourage storing personal data directly on blockchains and recommend keeping additional personal data off-chain whenever possible. And here I absolutely agree. And when on-chain storage is unavoidable, the guideline discusses several technical approaches. Encryption of personal data, maybe check if zero-knowledge proof would be possible, storing only salted or hashed keys, and use cryptographic commitments that prevent recovery of the original data once it's deleted off-chain, and this makes sense. There are 25 pages, lots of text, but there's one interesting sentence. It's the following here on page 24. Here, personal data needs to be erased or rendered anonymous in the event of an objection to processing pursuant to Article 21 or a request for erasure pursuant to Article 17 from the GDPR. So for blockchain, that means personal data needs to be encrypted, and on request, the keys need to be destroyed. That's it from my side. See you next week.